So now we are going to do an example radioactive decay problem. So in this problem, let's say that we have a sample of radioactive iodine 131. So iodine 131, 53, has 53 protons. And the mass of this sample is 682 micrograms. So micro, remember, is 10 to the minus 6. So 682 times 10 to the minus 6 grams. So what do we want to figure out? Well, there's lots of different things we could figure out. And what we're going to figure out for this particular problem is we're going to look at the activity. So first, we're going to try and figure out what is the activity at time equals 0. Okay, that initial activity. Okay, so we're trying to figure out this quantity, dN dt, or delta N over delta T at time equals 0. And as we just saw, this is equal to the decay constant, lambda, times N0, the initial number of nuclei, of iodine nuclei. All right, so how are we going to figure this out? Well, you'll discover in your textbook, when you go to do these problems, that there's a table in the appendix that gives you quantities that you can use. And one such quantity, and these would be things you would be given on an exam, of course. One thing they give you is the half-life for this particular nucleus. And the half-life of this iodine isotope is 8.0207 days. So it takes about 8 days for half of these radioactive nuclei to decay. So one thing to be aware of is that these half-lives come with all sorts of different time units, seconds, days, years. So you're going to have to be doing sometimes some time converting. For example, with activity, you usually want a number in decays per second. All right, how many decay per second? So we'll have to do some converting. But before we do that, first, let's look at our equation and say, okay, what do we need to know? Well, we need to know the decay constant, and we need to know our initial number of nuclei. So we can get the decay constant from the half-life. So what does that look like? We know that the decay constant is the natural log of 2 divided by the half-life. So it's the natural log of 2 divided by our 8.0207 days. And if you do that math, you'll discover that you get 0.08642 inverse days, or per day. So that's how many nuclei per day. Okay, so not very many, right? Okay, so so that's our, well, that's not how many nuclei per day. You have to multiply by the number of nuclei to get how many nuclei per day, but that's our decay constant. So, okay, now I'm going to leave that in inverse days, and I'm going to do my time conversion at the end. You can do the time conversion to seconds now, inverse seconds now, or you can do it at the end. It's your choice. So I'm going to do it at the end. Now, the other thing I need is how many nuclei I'm starting with, N0. So how do you figure that out? Well, you're going to use the mass that they gave you. And we're also going to use the atomic mass. So that's something else you get from the appendix in the back of the textbook if you don't have it already. So the atomic mass for this isotope is 130.906124. And it's in atomic mass units like we saw earlier. So we need to take this atomic mass and the mass that we were given and figure out how many nuclei. And the way you do that is it looks something like this. So the number of nuclei, we start with our 682 times 10 to the minus 6 grams. Okay, and then we remember from chemistry class that the atomic mass is how many grams there are in a mole of this particular element. Okay, and we're not going to worry about the electrons here. We'll just use that. So it's going to be 100, and so we're going to divide by 130.906,124 grams per mole. That's going to give me the number of moles I have of this isotope. And then if I multiply by our Avogadro's number, 6.02 times 10 to the 23, right, is the number of atoms in a mole, so per mole, that's going to give me my N0. Okay? And we typically, so you'll notice that the grams cancel out, the moles cancel out, and so we'll get a unitless quantity. It's just a number of nuclei, and in this case it's equal to 3.14 times 10 to the 18. Quite a few nuclei in this small sample. Probably not surprising, right? So, all right, so that's, we have our N0, we have our lambda, we can get our initial activity. So now that means, oops, move the hair out of the way. Okay, so what do we get? So our lambda is our 0.06420 inverse days. Okay, and our N0 is 3.14 times 10 to the 18. All right, and so we just have to multiply those two numbers to start with. Okay, and what do we get? We get 2.71 times 10 to the 17, and that's, we're going to put decays in here to remind us, this is decays per day. All right, but like I said, we typically don't want decays per day, we want decays per second. So how do we figure that out? Well, we're just gonna, we have decays per day here, so we have to convert our unit here, so we know that 1 day has 24 hours, and we know that 1 hour has 3,600 seconds in it. So if we multiply that through, we get that our initial activity is 3.14 times 10 to the 12th decays per second. All right, so quite a few decays per second. This is a pretty active source. Okay, I mean, what is that? That's trillions of decays per second here. All right, so, and that's because there's quite a lot of nuclei there, right? There's 10 to the 18 nuclei. So now we're going to do is say, okay, well, what happens to the activity over time? For example, what would the activity be? So what is dN dt at, say, time equals 1 hour? So if you wait an hour, what's going to happen? All right. So basically now we're going to go and look at how the activity changes with time, which we saw before. Okay, how does it change with time? It's just lambda N0, that initial activity, and then times e to the minus lambda t. So we have that exponential decay. All right, so on to our next piece of paper here. And we'll keep that so we can still see that at the top. Okay, give ourselves a little bit of light there. Great. Okay, so we have lambda M0 already. We just solved for that in the last part. So we just need to plug in lambda and time into our exponential to solve for this. Okay, so what's that going to look like then? It's going to look like this. So dN dt then is our lambda N0, 3.14 times 10 to the 12. And I'll worry about units at the end here. And then we're going to have e to the minus lambda, which is our 0.08642, right, inverse days. Right, okay, that's our lambda, and then the time is 1 hour. Okay, I realize that's only one sig fig there, but we'll assume we've got more sig figs. That I just did not write down. Okay, now one thing to be careful about here, really, really important, is the quantity in the exponent must have no units. So right now we have hours per day. We need to get rid of those units. So we basically need to convert our inverse days to hours. Basically we need to multiply by 1 day is 24 hours in the exponent there, and that will cancel out both the hour and the day units, and we'll get left with something without units, which is what we need. And so if we crank all this through, what do we get? We get 3.13 times 10 to the 12 decays per second. Okay, and you might look at that and you compare it. So if we look at this number and say, does that make sense? And compare it to what we had for the initial activity, we can see it's almost exactly the same. It's ever so slightly smaller, less than 1% smaller. But then if we remember that the half-life was 8 days, and this is only an hour later, so not very much time has passed. Okay, so this isotope has a long half-life, so it makes sense that it didn't change very much in only an hour.